Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 8, we are discussing about the biochemical conversion processes for biomass. But if you look at that, we have focused more on the pre-treatment stage because every biochemical conversion process requires the pretreatment. Especially if it is a lignocellulosic biomass, the lignin binds the cellulose and hemicellulose. And as long as lignin is there, I told you in some of the lectures that the degradation of biomass becomes very difficult. Therefore, the first step is to remove the lignin and hemicellulose, particularly if our feedstock is cellulose for enzymatic hydrolysis or any other biochemical route for high value chemical production. So the pre-treatment is a very essential and important part. Therefore, in lecture 4, we'll also continue with the physicochemical pre-treatment process like we started discussing in the previous lecture. And that will be followed by the enzymatic hydrolysis. In the previous class, we were discussing about the physicochemical process. Particularly, we discussed about a different kind of steam explosion process, liquid hot water process. Similar to a steam explosion, we have FX pretreatment process for biomass. So FX is actually for the ammonia fiber expansion, where it works more or less similar to this the steam explosion process. So we can say that it's a physicochemical pretreatment where biomass is treated with liquid anhydrous ammonia at 60 to 100 degrees Celsius under high pressure. Okay, and that is followed by a rapid pressure release. So that causes ammonia vapor expansion, and because of sudden expansion, there is a disruption that happens in the biomass fiber. So what happens? Firstly, the biomass, when we give the hot ammonia with high pressure, then it causes the swelling of the lignocellulosic fibers, and then it partially decrystallizes the cellulose. And when we expand it, the disruption of lignin and carbohydrate bonds happen, and deacetylation of hemicellulose also happens. Now, this causes the minimum solubilization of solids, particularly hemicellulose and lignin is mostly retained. It improves digestibility of biomass, and when digestibility improves, the enzymatic hydrolysis yield will definitely improve. It requires both cellulose and hemicellulose due to hemicellulosic retention, okay, in the biological process. So you have to remember these enzymes are required for biological conversion. So because it retains both hemicellulose and cellulose, so both kind of enzymes are required. Less inhibitors are formed, so less downstream processing is required for cleaning or something like that. Now, if we look at the application and stability, so of course, application is the obvious reason for all these pre-treatment methods is that we want to remove the lignin or we want to disrupt the biomass structure and make the cellulose easily accessible for the enzymes. Okay. Now, this ammonia expansion process or FX process, we can say, is highly effective for agricultural residue and herbaceous biomass, which is primarily lignocellulosic biomass, but it is less effective on woody and high lignin feedstock. Okay, that is something you have to remember. Okay, this has been successfully used for ethanol production and protein extraction. I mean, in the ethanol production and protein extraction process. So it is not used for ethanol production and protein extraction. Rather, it is in the ethanol production. It acts as a subset of the ethanol production process. There are different variants of the FX process. For example, we have 5X, which is continuous FX process via extrusion technology. Then we have ARP, which is ammonia recycle percolation that uses aqueous ammonia up to 5 to 15 weight% concentration at 140 to 200 degrees Celsius that helps to solubilize the hemicellulose. Then we have SAA, which is soaking in aqueous ammonia, which is conducted at 30 to 75 degrees Celsius. It retains both glucan and xylene. Now, the advantage of this process is that it causes high sugar conversion up to 90% under optimized conditions. It requires low enzyme loading, that is high efficiency, Okay, it is compatible with pentose fermenting microbes like recombinant strains, etc. But the major challenges are that ammonia, I mean, FX process is very complex, and especially ammonia is a costly material. We can't leave it, or we can't just throw it or discharge it to the wastewater. So we have to recover it, and that recovery itself is a complex process due to the volatility of the ammonia, and because of that, a very expensive and costly system for ammonia handling and recycling is required. In addition to that, the scale up demand energy efficient and cost effective configuration. Okay. Now, similar to ammonia, we have physicochemical CO2 explosion pretreatment process, wherein we use, like in steam and ammonia, we used H2O and ammonia. We replace the ammonia or steam by CO2, and it is also a similar process to that. Herein, we use supercritical CO2 to improve the digestibility of lignocellulosic biomass. We compress the CO2 at temperature which is above its critical points. Okay, and because of that, it attains liquid like density. Because of that, it facilitates the lignin removal and increases the cellulose accessibility. So what happens exactly is that when the high pressure CO2 goes in, it dissolves the water forming carbonic acid, and because of that, the auto hydrolysis of hemicellulose and lignin happens. And when autohydrolysis of lignin and hemicellulose happens, they get removed. The CO2 also gets into the biomass pores, and when there is a sudden depressurization, they try to come out suddenly, and because of that, they disrupt or break the fiber structure. Okay, and when fiber structure is broken, that leads to enhanced surface area, and when there is enhanced surface area, there is a improvement in the enzymatic saccharification. Now, if we look at the operational features of the CO2 explosion pretreatment process, it can be used with co-solvent like ethanol to enhance the delignification. It operates at low temperature compared to the FX process or the steam process like you have seen. It also avoids degradation of monosaccharides because the temperature is low. Do not use as any other toxic chemical. It is non-toxic, non-flammable and easily recoverable. Also, low temperature leads to low inhibitor formation compared to a steam explosion process. It is cost effective if it is integrated with the ethanol fermentation reuse route, because in ethanol fermentation you get the CO2. So if we can use that CO2, the raw material will be available from the production plant itself. Similarly, it is also effective for improving the enzymatic hydrolysis in several kind of biomass, I guess pen, pine, and other kind of biomass. But the major challenge is that these requires very high pressure. And when we have very high pressure requirement, we require a special kind of equipment with more thickness, and then MOC should be different. And because of that, when if we change the reactor material of construction or the thickness, the cost of equipment increases. In addition, it causes low sugar yield compared to the steam or ammonia explosion, because of course obviously that we have low temperature. Okay, and that's why it has very limited economic viability at industrial scale, particularly because of the low sugar yield and low effectivity. That again traces back to the low temperature of the process. So although it has several advantages, it is still not economically viable. Now let's talk about the enzymatic hydrolysis of the cellulose. So once we started, so like we discussed about the chemical, physical, then we discussed about the physicochemical. Now let's discuss about the biological processes which are required for enzymatic hydrolysis. Now, in this process, what happens that the cellulose enzyme, it plays a very critical role. Okay, what it does, it break down the cellulose into fermentable sugars. Okay, now the major type of cellulose are enzymes. So this is not cellulose, you have to remember these are enzymes. Cellulose is a polymer of glucose, but cellulose are enzymes. So the major cellulose are like endogluconesis, e.g. we have that cleaves the internal beta 1 4 glucosidic bonds in the amorphous region of the cellulose, and because of that it creates short oligosaccharides and it gets exposed to the attack by the different enzymes. Similarly, we have exogluconesis. It works on the reducing or non-reducing end of cellulose chains, releasing the celebobiose, which is a glucose dimer. Okay. Similarly, we have beta glucosidases, which hydrolyzes the celebobiose into glucose, and it plays a vital role in relieving the inhibitor or inhibitory effect of celebobiose on cellulase activity. And then the whole cycle gets completed. If we look at the glycoside hydrolysis GH families, then we have GH51, GH52, GH91, GH92. These all can break the internal beta alpha 4 glucan linkages. Okay. And now I told you when I was explaining about the structure of the cellulose, hemicellulose and lignin. So I said like in lignin we have beta O4. Here we have beta 1,4 glucanic linkages that holds the cellulose together. So if we break this bond, we will get the oligosaccharides. So we have endogluconesis, we have exogluconesis, we have beta glucosidase, we have glycoside hydrolase. That's a family of enzymes, and these all can help to break. And these all do not play the same role. Instead, if we look at the first, the endogluconesis, what it does, it breaks the beta 1,4 glucidic bonds. Okay, and that leads to formation of short oligosaccharides. Now, then after that, exogluconesis, what it does, it acts on the other end of the cellulose and convert that into the cellulose. And then beta glucosidases attacks on the cellubiose and converts it into the glucose. Okay. Similarly, the glucoside hydrolysis can also do what endogluconesis has done, that breaks down the internal beta 1,4 glucan linkages of cellulose. Therefore, what we will get is the small oligosaccharides. Okay. Now, these enzymes can also be used in combination with synergistic action can efficiently depolymerize both amorphous and crystalline cellulose and thereby producing the glucose for biofuel synthesis like ethanol. As you have seen already that the cellulose, what is happening, there are different kind of enzymes and different steps like endogluconesis, exogluconesis, beta glucosidases, glycoside hydrolase that breaks down. Similarly, for hemicellulose also, the degradation happens by hemicelluloses in a series of steps. Okay, so you can say that the enzymatic breakdown of hemicellulose involves multiple enzymes and multiple steps that should work in coordination, particularly the endohemicellulases, for example, endogelycinases or endomannanases. That cleaves the internal beta 1,4 glycosidic bonds, and when internal beta 1,4 glycosidic bonds are broken, what we get is the short chain oligosaccharides. So we'll get the short chain oligosaccharides, and then glycoside hydrolase like GH10 and GH11 can attack on xylan to release the xylo oligosaccharides. Okay. Similarly, we have accessory enzymes like acetyl xylan esterase, we have ferulic acid esterase. These remove the side chains like acetyl group or ferulic acid esters that further improves the access for core enzymes. Okay. Now, what happens that this synergistic activity with cellulase enhances the biomass, total biomass saccharification. Okay, if we put them together, this will help to improve the overall saccharification of the biomass. Okay. Particularly, it is critical for the biorefinery which is converting the lignocellulosic biomass into biofuel, particularly like ethanol, chemicals, and biomaterials, etc. The another method is the enzymatic degradation of lignin. So we looked into the like we have biomass, I told you. So may not be like not this. You can say this is, let's say my this is biomass. Here we have cellulose. So cellulose is broken by cellulase. These are the enzyme groups. And then we have hemicellulose. So these are disrupted by hemicellulase. And now, of course, then there are endogluconases, hemicellulases, like that kind of thing. So there are group of or series of enzymes. But then we are left with lignin. Okay. Now the enzymatic hydrolysis of this lignin actually requires lignolytic enzymes. Now, these lignolytic enzymes, what they does is that they degrade the amorphous and complex phenolic polymers of lignin into the smaller molecules. And you know that the lignin is the one that actually prevents the biological degradation of the biomass. So, if we have to convert the biomass via biochemical route into high value product, then we have to remove the lignin. Okay. So we use lignolytic enzymes. Okay. Now these are particularly the lignin degrading auxiliary enzymes LDA that enhances the degradation by producing oxidant such as hydrogen peroxide H2O2 or lignin modifying enzymes LME which directly depolymerizes the lignin. Now if we look at the LDA working and functions, what it does is that it has lytic polysaccharide monooxygenases LPMOs, which are like copper dependent enzymes that oxidatively cleave the glycosidic bonds. And then we have glyoxal oxidases, GLOX, which generates the H2O2 from aldehydes. And then we have aryl alcohol oxidase, AAO, which produces H2O2 by oxidizing the aromatic alcohols. Then we have pyranose 2 oxidase P2O, which produces again H2O2 from the pyranose sugars. Then we have cellobiose dehydrogenase CDH, which oxidizes the cellobiose, adding to LPMO activities. When we say LPMO, that means the lytic polysaccharide monooxygenate. Okay. When we have vinyl alcohol oxidation VAO, which oxidizes the vinyl alcohol to vanillin, that the vanillin, if you don't know, then you remember the vanilla ice cream that you eat is derived from the vanillin. Then we have copper radical oxidases like sucrose, which oxidizes alcohols and amines to generate the H2O. Okay. Now, if you look at this is a complex process. Okay. All of these enzymes, what they are doing, they are generating the H2O. Okay. Whereas the LPMOs is cleaving the glycosidic bonds. Okay. And so yeah, I would say like these are producing the H2O2, these are like oxidizing the vinyl alcohol and doing the oxidation activity. Okay. Then again this is producing the H2O2 and of course via the oxidation reaction. Then we have glucose oxidases, GOX, which oxidizes the glucose to gluconic acid and H2O2. Okay. Now, like we discussed about this LDA enzymes, we have another one is LME. In LME, the key LME enzymes and their functions are like the lecases, which is a copper containing oxidases that catalyze the one electron oxidation of phenolic compounds using the oxygen. We have lignin peroxidases, LIP, which oxidizes the non-phenolic lignin structures using the H2O2. We have manganese peroxidase MnP, which uses H2O2 to oxidize Mn2 plus to Mn3, which diffuses to oxidized lignin. Okay. And this whole thing functions via a redox cycle involving the intermediate compound 1 and 2. Then we have versatile peroxidase like VP, which is a hybrid enzyme that combines the activities of LIPs and MNPs. Okay, so what it does, like here it was oxidizing Mn2 to Mn3 plus, it oxidizes Mn2 plus and non-phenolic compounds directly. Okay. Now, why this is important? Because this enzyme works synergistically to break down the lignin complex bond. Okay. And their cooperative action is very much needed, or you can say it is necessary for biomass valorization and environmental bioremediation. Okay. Now coming to the point that what are the factors that affects the enzymatic hydrolysis. So of course one is the crystallinity of cellulose. This whole story of pre-treatment we have studied in 3 lectures just to understand that how the accessibility of enzymes to cellulose or accessibility of cellulose to enzymes is very critical, and the accessibility depends on what? The crystallinity of cellulose. So the major factors that affects the enzymatic hydrolysis is of course the crystallinity of cellulose, particularly the ratio of crystalline to amorphous region that affects the enzyme action. And crystalline cellulose fibers, which are linked to the non-covalent hydrogen bonds, enables easier enzymatic hydrolysis than the amorphous regions. Okay. Now the alkaline pretreatment, for example, if we use sodium hydroxide 14 to 18%, alters the structure, and when it alters the structure, the digestibility improves. Particle size, as I said, lower the particle size, better is the heat transfer. So it affects the kinetic diffusion, pretreatment efficiency, sugar yield, as well as the removal of lignin. A smaller the particle with higher surface area may pose handling challenge, while larger particles can lead to incomplete digestion. But relatively smaller particles are preferred if you want uniform heat transfer and better removal of lignin and hemicellulose. However, handling small particles is a very challenging task. So trade-off between the particle size and handling complexity has to be developed. Okay. The methods for particle size, I have already discussed the grinding, milling, extrusion, etc. Okay. Now, the accessible surface area and pore volume are very important because the enzymes has to penetrate into the cellulose for its hydrolysis. So the hydrolysis improves with the larger pore and higher ASA. Okay, or we need a higher accessible surface area and large pore sizes for enzymes to access the cellulose. And the pre-treatment methods significantly affect the surface area. As I told you earlier, like how it creates the porosity and how it improves the accessibility to the cellulose by enzymes. Also, the particle size, the crystallinity, and the enzyme adsorption capacity, and which overall affects the hydrolysis efficiency. The degree of cellulose adsorption, high cellulose adsorption is there, then by default there will be high hydrolysis. However, non-specific binding to lignin reduces efficiency. We are discussing about the factors affecting the enzymatic hydrolysis. So one is crystallinity of cellulose, particle size, ASA and pore volume, degree of cellulose adsorption, then we have pre-treatment of biomass. So depending on what kind of pre-treatment method, whether physical, chemical or biological have been used and what kind of disruption has happened, whether the lignin is completely disrupted or not, whether the surface area has increased or not, becomes a very important factor. In addition to that, economic factors such as the energy demand, equipment durability, chemical cost, etc. are another important factors that affects overall enzymatic hydrolysis. So for example, the steam explosion needs high pressure reaction, while acid hydrolysis involves high chemical uses. So you always have to find a trade-off. You will always have a situation where you have to trade off between the two values. Okay. Then inhibitory impact of lignin residue. If the residual lignin binds enzymes non-productively and releases the phenolic inhibitors. Now this inhibitory mechanism is like can be competitive inhibition, irreversible binding, or enzyme denaturation. We can use the mitigation strategies to prevent the inhibitory mechanism, like we can use physical, chemical, or biological pretreatment and use of additives like activated carbon. Similarly, we can use additives such as surfactants and chelating agents for hydrolysis to enhance the enzymatic digestion or hydrolysis and to reduce the non-specific binding. But then again, what kind of additives we are choosing, that will affect the overall performance of the enzymatic hydrolysis. Besides that, the degree of polymerization, particularly for cellulose, if it is more crystalline, resistant to enzymatic attack, then it will be a problem. So low degree of polymerization cellulose is more amorphous and accessible. Then the other process or biological conversion process is fermentation. Okay. Now in fermentation, what we do, so we have now pre-treated biomass. So you can see here, this is biomass. And pre-treatment we have learned in so many classes. Then we have learned about the enzymatic hydrolysis. So now once we get the sugars, we have to make a value added product. And for that, we do fermentation, particularly, I mean, in most of the cases, microbial fermentation to produce the ethanol, lactate, butanol, acetone, acetate, or succinate, etc. Okay. So fermentation is a microbial conversion of sugars, particularly the glucose and xylose that has been obtained from the lignocellulosic biomass into the product such as ethanol, butanol, lactic acid, acetone, etc. What happens once these soluble sugars are produced? There are a wide range of natural biocatalysts which can ferment the sugars into the lactic acid, particularly the species in genera Lactobacillus, Lactococcus or Streptococcus, Pediococcus, and others. For ethanol, I mean fermentation of sugars to ethanol, we have Saccharomyces cerevisiae or S. cerevisiae we looked earlier. Gimonas mobilis, we have Pichia stiptis or biocatalyst we can use to convert this sugar into the useful product via fermentation process. If we have to produce butanol, we need Clostridium acetobutylicum, we have Clostridium bajernsky. So lot of, I mean, these are some examples, but lot of things can be there. Okay. Now, similarly, we have different multi-phase fermentation approaches for following the cellulose hydrolysis. For example, we have separate hydrolysis and fermentation unit. So these are like two-step process where the steps are conducted sequentially in separate reactors. Okay. So firstly, cellulose is hydrolyzed to glucose and then fermented to ethanol. Now, advantage here is that we have independent temperature optimization for enzyme and yeast. But the problem is the product inhibition due to sugar buildup in like syllabiotes or glucose, or higher capital cost due to double reactor which are required, and risk of contamination during the prolonged hydrolysis. To overcome such limitations, the simultaneous saccharification and fermentation process SSF has been developed where the hydrolysis and fermentation both happens in a single reactor. So glucose is released by the enzymes immediately, and as soon as the glucose is released by the enzymes, it is consumed immediately to prevent the inhibitor formation. Now the advantage of such process is the lower enzyme doses because all of process happens very rapidly, the high ethanol yield and simplified operation. Whereas reduced contamination because of the low inhibition formation and equipment cost. Okay, but the problem is if ethanol starts getting accumulated, the enzymes deactivates frequently. Okay, And then also there is a mismatch in the optimum temperature for hydrolysis and fermentation. Now for that, what we do is that there is another process which is called pre-saccharification and simultaneous saccharification and fermentation, which is PSSF. Now in this, what happens in the same reactor? Firstly, we do the saccharification for few hours, and that is followed by the simultaneous saccharification in the same reactor. Now what it does, it allows the enzymes to work briefly at their optimal temperature before yeast is introduced. Now the major advantage of this process is that it prevents glucose buildup and enzyme inhibition. It is cost effective. It leads to better yield than SHF and SSF. But the problem is that it requires longer reaction times. Okay. Similarly, we have continuous flow fermentation. And in continuous flow fermentation, what we do is that we continuously charge the hydrolysate and remove the ethanol. Okay. So this kind of process uses mostly immobilized cells for reuse and process stability. The advantage, of course, when there is higher continuous process, this will have continuous production, so higher production rate, high ethanol productivity. And then we have drawbacks like complex process control and long-term maintenance, etc. Another important product which is obtained by the biochemical route is succinic acid. So same we do here, we take the biomass, we do the pre-treatment. Now the pre-treatment includes the hydrolysis production, lignocellulosic hydrolysis, and then that is followed by the microbial fermentation of pentose or hexoses. So if you can see, we can apply all the processes. For example, separate hydrolysis and fermentation process, SHF. We have simultaneous saccharification and fermentation process, which is SSF. We can make, so here we can take the biomass, we can do hydrolysis and then saccharification, and we can get the xylose. We can use SSF, we again biomass, and then in one step the saccharification and fermentation to get the xylose. Or we can do simultaneous saccharification and co-fermentation, like you can see here. In this, everything is happening all together, so we get the pentose. Here also consolidated bioprocessing, CBP, we get the pentose and we get the hexoses. Now using these we can make the succinic acid. Okay, we'll discuss why succinic acid is important. Okay, but the biochemical processes also yields very important and very high value chemicals. Okay, for example, if we look at the application of succinic acid, it is used to produce lot of chemical raw materials. For example, butadiene, butanediol, digoxin. It is used to produce resins such as malic acid, maleic anhydride, aspartic acid. It is used to produce medicines, pesticides like sacchinamide. We have two pyrrolidone, we have tartaric acid, and solvents like furanidine, we have butanediol, we have oxalic acid, or we can make food additives like aspartic acid, succinic anhydride, or itaconic acid, etc. Another biochemical or biological conversion process is anaerobic digestion. We will have next 2 weeks particularly discussing about the anaerobic digestion. But this is all for today's class. See you in the next class. Thank you.